Good afternoon. I'm Hamed Okravi from MIT Lincoln Lab. Today I'm going to talk about an attack that we performed against a memory corruption defense called code pointer integrity. This is joint work with my students on the first line and my colleagues on the second line. So at the beginning, I'm going to tell you what you will see in the rest of the talk. So this is the bottom line up front slide. There was a technique that was proposed at OSDI last year. It's called the code pointer integrity. It was developed by teams at EPFL, UC Berkeley, and Stony Brook University. It's a memory corruption defense. In this talk, we'll show that some of the assumptions made in the technique are unsound. And in fact, specifically, the reliance on information hiding is not a sound assumption. And we show a fully functional attack that can bypass the technique in a matter of seconds. So first, I would like to give you a quick overview of the type of attack that we're talking about. You heard a number of overviews in this session, but just quickly, a memory corruption attack looks something like this. When we ask a machine to copy a piece of data, A, to a buffer C, it does so. Unfortunately, when we ask it to copy data B, which is now larger than the buffer, to the same buffer C, it still does so. But it corrupts adjacent values after the buffer. So what could be stored in those locations? Well, as it turns out, there can be important data values such as function pointers or return addresses or function arguments stored there. And by overwriting those values, an attacker can hijack control of the machine. And this is the basis of a memory corruption attack. Now, in the past, this was done by redirecting execution to a maliciously injected code, otherwise known as code injection. Now, because of the defenses such as data execution prevention or WXOR or non-executable memory, this is usually done with code reuse attacks or ROP attacks. But the principles are the same. So this is an example of a control flow hijacking attack where we are asking for a username from a user, and the address of a function process user is stored right next to that username. So if the user provides a username that's longer than the buffer for the username, they can corrupt the value of the function pointer. And if they're smart in their injection, if they put the address of a different function, let's say delete user, they can overwrite the function pointer and redirect execution to delete user. And a nice way of describing this type of attack is this text that says, because the source and destination of data movement is not properly checked, an attacker can corrupt the values and hijack control. Now, would you like to take a wild guess which decade this text was written in? It was actually written way back in the 70s. So as a matter of fact, 1972. So we've had this problem for 5 decades in computer science. And we still have it today. And partly because defenses that are efficient that are preventing memory corruption attack and are efficient are actually hard to design. But we do know how to solve this problem. If we provide complete memory safety, it's going to prevent all of these type of attacks. And complete memory safety refers to 2 properties. The first one is providing spatial pointer safety, meaning that the pointer can point to some locations, but not other locations. So by enforcing that, we can ensure that the function pointer cannot be redirected. The second property is temporal pointer safety, meaning that a pointer may be able to point to a location, but after some time, when that location is holding some other data value, the pointer is not allowed to point to that location. And there are techniques that have been implemented in the community that provide complete memory safety. For example, the softbound technique plus its sets extension. It provides complete memory safety. Unfortunately, for unmanaged languages like C, C++, that comes at a high cost, more than 100% overhead usually. And that is the motivation why researchers have looked at lighter weight techniques to enforce memory safety. And code pointer integrity is one of those lighter weight techniques. And the concept behind it is actually fairly simple. They enforce memory safety checks, but only on code pointers. So in this case, they don't protect data values or data pointers, but they do protect code pointers, the process user example that I mentioned. So if we look at the spectrum of possibilities, at the very left end, we have the status quo, no memory protection. which is really bad, easily attackable. And at the very right end, we have complete memory safety, but it is slow, more than 100% overhead. CPI is actually somewhere in between. It provides some of the guarantees of complete memory safety, but with much lower overhead, less than 10% on average, although for some of the benchmarks it's higher. There's another variant of CPI called code pointer safety, or CPS, which doesn't protect pointers to pointers. So it's a weaker security guarantee, but with lower overhead. But in our attack, we attack the generalized technique of CPI itself, so we won't talk about CPS any longer. So let's look at how CPI works. The concept behind it is actually fairly simple. They take any code pointer from the code and replace that with an index to a region of memory, which is called the safe region. So in this case, the address of process user function is replaced with a reference into the safe region, let's say in this case, slot number 6. And again, this is a simplified view of what CPI is. So more specifically, the base address of the safe region is added to any function pointer to get a reference into that safe region. And the safe region is somewhere inside memory, along with other regions of memory like a stack or heap. So the important question is, how is the safe region protected? Because it is the treasure trove of information, and if an attacker can leak the safe region or modify the safe region, then they can bypass a technique like CPI. In the current implementation, for 32-bit x86 architecture that supports segmentation, CPI actually uses segmentation to protect the safe region, which is reasonably secure. But for architectures that don't support segmentation, like 64-bit versions of x86 or ARM, it relies on information hiding and randomizing the location of the safe region inside memory. So by hiding that safe region inside memory, that is how it is protected in CPI. But if ASLR is weak because it can be leaked and attacked, the question is, can CPI be attacked the same way? In order to answer that question, we have looked at two implicit assumptions behind the CPI technique. The first one is that in CPI, they specifically make the point of removing any reference from the code to the safe region so that those references or pointers cannot leak. And the assumption there is that if there is no pointer to the safe region, its content cannot be leaked or maliciously modified. And the second assumption is that leaking large parts of memory requires prohibitive number of crashes. So this is against servers that would respawn upon crashing, which is important, for example, for web servers, because if they crash and if they don't respawn, that would hurt availability. So for servers like Nginx or Apache that would respawn, an attacker can cause many crashes and still attack the server, but then that may be detected by our defensive mechanisms. So we have looked at these assumptions one by one. The first assumption is actually not correct, and we showed that in a CCS paper last year, that information not only can leak directly, but it also can leak indirectly using side channel attacks. In this case, an attacker can redirect a data pointer, a dangling data pointer, to an arbitrary location in memory without actually having a prior knowledge of where that location is. And by monitoring side channel information remotely, an attacker can leak the content of memory. And this is how it works. So on the left side, you have Nginx running, for example, one server. And there's a loop that depends on the value of a pointer, data pointer in this case. And on the left side, you have, the server is on the right side. On the left side, you have the attacker. Now, if the attacker corrupts a value, the value of that data pointer, n, to point to some arbitrary location in memory, the runtime of that loop would depend on what value the pointer is pointing to. So in this case, the attacker sends a request, corrupts the value of n to the first location in memory, which is 0, and gets a response back. And based on the timing of the response, they get a point in that chart of delay versus request number. If they repeat that experiment, corrupt the value of n to the next location, they get another delay, which is a little bit higher, because in this case, the byte value is 5, for example. If they repeat that, the next value is FF, or 255, they get a larger delay. And by monitoring these delays, an attacker can leak information without having a prior reference to that location in memory. So the first assumption is incorrect. What about the second assumption? Leaking large parts of memory requires prohibitive number of crashes. We actually show that that assumption is also incorrect. We have developed two attacks that can find and maliciously modify the safe region. One is a non-crashing attack that's slower, and the other one is a crashing attack that is much faster. So I'll talk about how these are done. So I'll talk about the non-crashing attack on the left side first. In this case, we are interested in finding the base address of the safe region. Because if we know the base address of the safe region, we know the location of any pointer information, the metadata that's stored to protect those function pointers. And we can modify them using dangling data pointers. So how do we do that? We first redirect a pointer into some arbitrary location inside the safe region. And this is a data pointer, so it's not protected by CPI. You might ask, how do we ensure that the process doesn't crash by just redirecting pointer to an arbitrary location? Well, as it turns out, the size of the safe region is actually much larger than the entropy in the base address of the safe region. So in the default implementation that it uses system ASLR, the entropy in the base address is 28 bits of entropy, whereas the size of the safe region is 2 to 42 bytes. So the safe region itself is much larger than the base address entropy, and because of that, there are certain regions that are always allocated. And by redirecting a dangling data pointer to those locations, we can be sure that the process doesn't crash. Now, how do we find the base address based on that? Well, as it turns out, other libraries are linked on top of the safe region, in the mmap region of the process. And our intuition is that, let's say the top library is libc. If we jump ahead, if we move to the top by the size of libc, we can be sure that we will never fall off the edge and cause a crash in the process. So the second scan happens size L above the first scan. And L, again, is the size of libc, and this is a simplified view of it. And then the third scan happens size L above the second scan, so on and so forth. And after we repeat this n times, we'll land into libc, and then bingo, the attack is done, because now we know the base address of the safe region, and we can arbitrarily modify it. For the details of how we distinguish between pages inside the safe region and libc, please refer to the paper. There are a lot of details involved in the attack. But this attack takes actually more than 90 hours, because there's 500,000 of these scans that should happen. The safe region is very large. So we wanted to actually implement a faster version of this attack as well. And that is the crashing attack that I'm showing on the right side of your screen. So here, the first page scan happens in that same always allocated region. So it is still not causing any crash. But then the second scan happens way top in the memory. So it causes a crash, most likely, because those regions are not allocated. And then for the third scan, we come down again and scan some region inside the safe region. For the fourth scan, we can go above in the address space in memory, cause a crash. So what we're doing is a binary search, essentially. And after doing so many scans, we'll eventually land inside libc at the kth scan, and then the attack completes. And this can be done much faster than the other attack. So the question is, can this attack be prevented easily? Or is there something that can be done fairly easily to prevent our attack? Well, we have looked at those options, and we have evaluated them in our paper. I'll refer you to the paper for the details of it. But I'll just quickly go over a number of them here. So the default implementation relies on system ASLR, which has 28 bits of entropy for the start address. But what if we don't do that? What if we allocate the entire mmap or use the entire mmap region, the entire region that's available to us, which is roughly 47 bits of addressable space, and then randomize the location of the safe region there. So instead of just having a little bit of entropy, we can use the entire address space. That is possible, and in that case, the non-crashing attack will be stopped. We cannot do this without causing a crash. But the crashing attack is still possible, and on average, it will cause 16 crashes for this, even with this randomization. Another possible defense against the attack is to make the safe region smaller, because a large part of the attack was that safe region was very, very large itself. And we have looked at that option as well. There's another implementation of CPIs called the hash table implementation. That is slightly different than the simple table. So we have looked at what is the minimum size that is possible for that hash table size. And we have evaluated 2 to the 33 size, 2 to the 28 first, sorry. And for that size, the spec benchmark actually did not complete. Some of the programs in the spec benchmark failed to provide the correct result. So we started to increase the hash table size to the minimum size that's necessary to complete the entire spec benchmark. And that size is 2 to the 33 bytes. So that's the minimum size that's necessary. And again, in that case, the non-crashing attack will be stopped, but the crashing attack is possible with, on average, 8,000 crashes. So now the number of crashes grows. So actually, I have a demo of this attack. Let me just quickly show you. Okay. On the left side, you're seeing the Nginx. We have implemented this attack against Nginx. I'm specifically showing you the error log of Nginx. So if I cause a number of crashes, you should see some entries in the error log. And on the right side, I have 2 worker processes that are running on the attacker machine. So the right side is the attacker machine, the left side is the victim's machine. And if the attack is successful, I should be able to get a shell in that window pane at the bottom. So when I run the attack script, you should see a number of crashes, then a number of bytes scanned, then it will be ready to deploy the payload. And as soon as I deploy the payload, it will corrupt a function pointer inside the safe region and hijack control. So let's run it. Crashes, byte scans, done. So right now, it caused 10 crashes with 110 byte scans. So let me actually deploy the exploit. Exploit deployed. There we go. I got a shell on the machine. I can run whatever command I want, ls or user add, or other commands. And as you can see, it caused 10 entries in the error log of Nginx, which said the thread crashed. Okay. So to conclude, in this talk, we showed that information hiding in memory is not an effective defense. And that's how systems like ASLR are bypassed. And even state-of-the-art techniques like CPI can be bypassed by more sophisticated forms of information leakage. Now, I have to mention that CPI does certainly raise the bar, because now I have to attack CPI and then attack the machine. But we believe that the true cost of preventing memory corruption attacks is actually very high. And some of the more promising defenses in the community are those that are looking for hardware extensions that can facilitate or make complete memory safety checks faster. The pump talk that you heard in this session, earlier in this session, and the cherry talk that you heard on Monday are some of the more promising defenses that can prevent this type of attack in an efficient manner. Lastly, I have to mention that this work was only possible because the CPI team has graciously agreed to share their implementation, which is much more than many would do in the community. And we are really thankful to them for doing so. We have been in contact with them with long email exchanges that have been very constructive for both of our teams. They mentioned to us that they are working on a software fault isolation-based implementation of CPI to protect the safe region. And we believe that that's a great idea to move away from information hiding and use stronger defenses. We would love to see an implementation of the CFI-based technique. Some of the previous SFI-based techniques have had larger overhead, so we would love to be able to evaluate this new implementation of CPI as well. But we are really thankful to them for collaborating with us and sharing their implementation. Thank you.
Time for one quick question, then lunch.
Hello. So I am Volodymyr Kuznetsov from EPFL. I am one
A
of
little
the...
louder, please.
I'm Volodymyr Kuznetsov from EPFL. I'm one of the authors of CPI work. So yeah, we did some email exchanges with you. And so yeah, thanks for the work on you analyzing the information hiding based implementation of CPI. But I'd like to point out that it's just one of the implementations that we released. So we released, and so in our original paper, we also described the SFI-based implementation. We did not start working on it now. It existed all the time. And also, even among information hiding-based implementations, we also have stronger implementations than the one you attacked, right?
So we have evaluated all of the implementations that were available to us, which were 3 of them: simple table, hash table, and subtable. And only hash table and simple table provided the correct values. And we evaluated those, and we have all the numbers in the paper. We have also evaluated other options that are possible that were not implemented to make the implementation stronger. And yeah, we would love to see the SFI implementation as well.
Oh yeah, you can download it now from the website. So I think that it's a good reason to file a bug report for CPI. So we would welcome getting a bug report on our issue tracker about the bugs that you found in the implementation. But I do not think that a vulnerability in one of the implementations warrants the claim that CPI as a technique is broken.
Right, and we are not making that claim. We are evaluating different implementations, and we are trying to understand what is the effectiveness that CPI provides and what it takes to bypass them. We're actually not making any judgment call as to whether or not you would be able to detect that many crashes or this many crashes, or how difficult it would be.
Okay.
All right, thank you.
Yeah, I think just follow up with Vova's comments. I think it's important to note that the CPI, so essentially the work is only focused on actually the simplest implementation for CPI. And we actually, I think Vova's poster yesterday has showed numbers for the other implementations. It will take at least, for example, 50,000 crashes for some of the implementations to actually, for the attack to work. And also CPI as a design, it has a essentially has a theoretical properties, and the attack essentially is only on one of the simplest implementation, and it's not on the CPI's design.
Thank you for your question. As I mentioned, we actually do evaluate all of the implementations that were available to us.
And
which
again,
were the hash
I
table
think some of this is,
Maybe
again, it's a
this
research
offline?
prototype. So the implementation, of course, some of the implementations may be buggy and so on. And Vova has done a great work in actually making it open source. And we welcome the community to actually help improve the open source.
Sure. Let's take the rest of the discussion offline.
Yeah, let's take the session offline. It's lunchtime.
All right. Thank you.